Morning, folks. Today we are going to move on to the third section of trigonometry. Whee! Sine and cosine values. I don't know, it's kind of a weak title. Basically what we're doing here is we're learning how to take any x comma y in the coordinate system and do some trigonometry there. And I think that I'm going to ignore the order of things here, and I'm going to start having us work with the reciprocal functions as well. That way, when we do actually introduce them, they're not brand spanking new to you. I want you to be comfortable with them. Cool beans? You guys cool with that? Also, I didn't look ahead before I was teaching this lesson to the period 2, and I felt the need to explain something. And then it turns out it showed up at the end of the lesson anyway. But some people were struggling with why things were called co this and co that, and not knowing which one was which and things like that. I think I explained it once before, but the reason why we use secant for the reciprocal of cosine, but we use cosecant for the reciprocal of sine. I know that's annoying to some people. Heck, it's annoying to me. But the reason why is because of geometry. Geometry was around long before trigonometry was discovered. So, we've got a circle here and some things drawn. A line that touches the outside of the circle but without going through it, this is called a tangent line. And that name was there in place long before the trigonometry was discovered. And when they started slapping right triangles down on these things, they found that the measurements of these pieces of the triangles actually were exactly the y value over the x value of other things that they were doing. They said, oh, well, if that function goes along with that fraction, we've already named that structure, we'll just call it the tangent function. So that's how that came about. Geometry, a line that passes through a circle twice that is not the diameter, is called a secant line. So we have tangent lines, we have secant lines. And when they started doing the trigonometry, they found that lengths of secant lines corresponded with the reciprocal of their cosine function. So that is why it was named secant. So then the question becomes, then why was the other one named cosecant? And the answer is actually a question. Why is it named cosine? You see, it's not an accident that you have a sine function and a cosine function. Grab a piece of scrap paper here. So this kind of spills the beans a little early, but I think it's important that we can have a clearer understanding of why we have cosecant and secant. See, in your mind, you had sine, right? And then you thought, well, why not call the other one cosine? But it's not an accident that it has the word sine in its name. It's because when you're talking about functions, this CO prefix, at least in mathematics, has nothing to do with like it does for cooperate or coterminal even. When there are adjectives like that, coterminal, that describes two things that are landing in the same spot. This is literally a co-function. And this prefix is the same prefix as complementary. And the reason why it was chosen, let's take a 30, 60, 90 real quick. 1's always across from a 30. We've got a root 3 here. We got a 2 here, right? If I asked you to do the sine of 30 degrees, it'd be y over r. But if you were standing here, this is not your... If you were standing here, this isn't the opposite side like it was for the 30. This is the adjacent side. So if you're standing here at the 60 and you do adjacent over hypotenuse, you get the same value. So when they were setting up the ratios and naming things, clearly you have the sine function. Fine. What we found out real fast, I say we like I was there, right, when they were discovering the mathematics, is that this fraction can be attained as well if you're standing at the complementary angle. So the cosine is literally the complementary function to the sine function. Sine and cosine are equal to each other at complementary angles because of this setup. Look, I don't know what sine of 10 degrees equals, at least as a number. But I do know that it's the same as the cosine of 80 degrees because those are complementary angles. So the complementary functions are equivalent there. So once we've named a function, sine, we found out complementary function, fine, cosine, did some more mathematics, and found out that the lengths of our secant lines correspond to the reciprocal of cosine. So we go, okay, fine. Secant is the reciprocal of cosine, but just like cosine is complementary to sine, secant has a complement as well, the cosecant, which turns out is the reciprocal of sine. So that's why they're named that way. I know sometimes it's annoying, but I figure it helps to know the history on it and at least know what we mean by the co thing. Okay? And the same thing is going to happen for tangent and cotangent. The tangent of 30 degrees is y over x, or opposite over adjacent, 1 over root 3. So if you're here and you're trying to get 1 over root 3, then you have to use adjacent over opposite, the cotangent. So tangent and cotangent are equal to each other at complementary angles, reciprocal functions. Cool beans? Awesome. Great. Boop. So today we're going to be doing trig at wherever the heck we feel like it in the 4 quadrants. Cool? And we're not even going to have special angles. So we're not going to have our pi over 3s or pi over 4s or pi over 6s. No, just some wild, wacky place. We've got the coordinate -5, 3. It's in quadrant 2. In quadrant 2, x's are negative, y's are positive, right? Drop a triangle here. And we're going to perform some trigonometry here. I know it doesn't make any sense in, the real world or anything like that, but I have a triangle that essentially has these side lengths. Can a triangle have a negative side? No, it can't. But this is trigonometry, okay? We've been asked to find sine and cosine. Not only are we going to find sine and cosine, we're going to find their reciprocals as well because I want you used to doing that. Sine and cosine are both going to require the radius of my circle though. How am I going to get this length? Pythagorean theorem, sure. So the Pythagorean theorem would have been a squared plus b squared equals c squared, right? But I want to make it more triggy than that. Instead of saying a, b, and c, let's use x, y, and r. I mean, we already need to be getting used to that anyway instead of saying SOHCAHTOA, right? So instead of saying a squared, why don't we say x squared? And instead of b squared, let's say y squared. And instead of c squared, since it's the radius of a circle, r squared. By the way, this is the equation of a circle that is centered at the origin. You're supposed to have learned that in geometry. X squared plus y squared equals r squared. Newsflash. Equation of a circle is literally just the Pythagorean theorem. Distance formula, literally just the Pythagorean theorem. You're going to be shocked how often the Pythagorean theorem shows up in mathematics. It's all over the place. But anyway, let's use x, y, and r. So x squared plus y squared equals r squared. Let us track down our radius. Please use parentheses. If you don't use parentheses on the AP exam, right here, if you just written -5 squared, no parentheses, you will be wrong. So don't do that. Yes, you have to show your work on the free response stuff. Yeah. So make sure that you use parentheses because they'll mark you wrong, okay? Radius is the square root of 34. There we go. We're ready to rock and roll. Sine of theta, y over r, 3 over square root of 34. The reciprocal function to sine is cosecant. Literally, flip the fraction over, r over y. So yes, I'm doing that early, but we might as well. So this is cosecant, CSC. I was talking to my friend who teaches AP Pre-Calc and AP Calculus up in Gainesville, and I was like, hey, what do you think about rationalizing denominators? And he said, in the free response type stuff, clearly this is a correct answer, so no, you're probably not going to have to rationalize denominators. And I think he's right about that. I'd say in the free response, he's right. But I'm also worried that in the multiple choice, this would not be an answer waiting for you. I fear that in the multiple choice, they're going to rationalize their denominators. It's not that hard. You just multiply the top and bottom by the radical. So what we would get is 3 root 34 over 34. So I believe he's correct. When material is given to you, it'll be given to you rationalized. And if it's multiple choice, it'll be rationalized. If it's free response, you're probably not going to have to rationalize. Just be comfortable knowing how to rationalize. Let's find cosine of theta. And I don't know if you noticed, but I used the 3 and the root 34, which are not even part of angle theta. I mean, root 34 is, but theta is out here. To do the trigonometry, we referenced this angle. We used the reference angle and the reference triangle to do our trigonometry. That's why it's called that. Cool? All right. Cosine x over r, negative 5 over root 34. And the reciprocal of cosine is secant. Flip the fraction over. If cosine is x over r, secant is r over x. Since r could never be negative, this shows you that x was negative. Not bad, right? Questions, comments, concerns? Anything I can help you with? Easy peasy? Okay. Screw it up. Theta is an acute angle. What does that instantly tell you? Less than 90, which would force us into quadrant 1. So we didn't need to be told that theta is in quadrant 1. Just saying it's acute forces it into quadrant 1. If it didn't say any of that, if it just said, hey, let sine of theta be 5 over 6, that's possible in 2 different quadrants. Because sine is y over r, it would be positive in 2 different quadrants. And we would have to draw that triangle in 2 different places. Might be a skip in the video. I had it paused, and I think I moved my paper when I stood up. And I don't know. Whatever I was saying. Yeah, if it hadn't said quadrant 1, then I would have to draw the 2 places where sine is positive. Remember, sine is positive when y is positive. And that would have occurred in quadrants 1 and 2. But we were told acute, so no big deal. We'll draw it in quadrant 1. Sine is y over r. And in order to figure out cosine and tangent, as well as their reciprocals, I'm going to need the x value. To fill out what we know. We don't know x. Please use parentheses. Subtract 25. You get x squared is 11, so x is root 11. What if I had been in quadrant 2? then what? Then it would have been negative root 11 for x, correct? Because in quadrant 2, your x values are negative. So we always want to keep that in mind. That's why I always draw my pictures. I'm going to be real, I can't do trig without a picture. I have to draw a picture. We're ready to rock and roll. Cosine is x over r, root 11 over 6. The reciprocal of cosine, secant. Just flip the fraction over. 6 over root 11. Again, if it's multiple choice, I don't think 6 over root 11 would be something for you to choose. You'd need to rationalize it to 6 root 11 over 11. Just multiply the top and bottom by root 11. If it's a free response, I think you can get away with it. What else? Oh, tangent. Tangent theta is y over x. So 5 over root 11. Again, I think you'd need to rationalize that for multiple choice. It'd be 5 root 11 over 11. And the reciprocal of tangent is cotangent. Flip the fraction over. So we have CSC for cosecant, the reciprocal of sine. SEC, secant, the reciprocal of cosine. COT, cotangent, the reciprocal of tangent. And the whole co-things hold true. Tangent and cotangent equal at complementary angles. Secant and cosecant equal at complementary angles. Sine and cosine equal at complementary angles. That's what the co stands for. Good deal? As I see that being an AP question on a no calculator portion, asking you to evaluate at a crazy angle, and you don't need to actually evaluate, you just set it equal to a different trig function. What do you think? Doing okay so far, so good? Yeah? Next, we're told that our angle, theta, is in quadrant 3. But tangent there is giving us 4 over 7. So let me draw my angle. Tangent's y over x. Good? No. No? Why? Negatives. Ah, negatives. That's right. In quadrant 3, x and y are both negative. But that's why tangent is positive there, because it's going to compare these two negative numbers. Good. Alrighty. Again, going to need the radius, though, if I'm going to find sine, cosine, and their reciprocals. Please use parentheses. Negative sine squared is 49. Negative sine squared. Negative 7 squared, excuse me, is 49. Negative 4 squared is 16. R squared is 65. So our radius, which is always positive, will be the square root of 65. There you go. Trying to make it so that I'm not in the way. There we go. Okay. Sine and cosine. Sine of theta. Y over r. Negative 4 over root 65. You want to rationalize that? Fine. Multiply the top and bottom by root 65. Negative 4 root 65 over 65. The reciprocal of sine is cosecant. That's what? R over y? Yeah, R over y. Cosine x over r, negative 7 over root 65. Reciprocal of cosine is secant. Flip the fraction over. There you go. Yes? The shortcut for sine. The word sine is S-I-N-E. Because if you're not going to shorten one, you shouldn't shorten any of them, right? Well, cosecant is a lot of letters. That's why. It does kind of seem dumb to shorthand a word by just removing one letter, but it's because we're just trying to make them all similar and just use 3. Okay. It's not bad, is it? Yeah, he says easy. Yeah, I'm glad you think so. No. I'm serious. I'm glad you think so. That sounded sarcastic. It's not meant to be. So you know what this is? This is the stuff that I already do, and I've already trained you to do. I don't worry about the unit circle. I draw 30, 60, 90s with those ratios. I draw 45, 45, 90s with those ratios, and I move on with my life, okay? Now, those are going to be the special angles for us. The 30 degrees, pi over 6. 60 degrees, pi over 3. 45 degrees, pi over 4. Of course, all the 90s are pi over 2s. So we're going to get used to those things, all right? You could take the time to memorize all of these, or you could do what I do, and that's just draw circles, or triangles. Let's draw them. I don't have a lot of space, so I'm going to squeeze them in here, okay? We'll draw one for 30. In fact, the triangle is so small, I'm going to put 30 degrees outside the triangle. I just can't fit it inside. We say there's always a 1 across from a 30. That means there's a root 3 next to it. There you go. The 45. Again, I'm drawing them so small I can't fit my numbers inside the triangle. 1, 1, root 2. And the 60-degree angle, none of my pictures are drawn to scale. If the 1's always across from the 30, then the root 3 is always across from the 60. And we're ready to rock and roll. All right. Sine of 30 degrees, sine of pi over 6. Y over r, opposite over hypotenuse, 1 over 2. Let's work the same triangle. Cosine here, x over r, root 3 over 2. And tangent at 30, y over x, 1 over root 3. Then we can head on over to the 45-degree angle here and say sine y over r, 1 over root 2. Again, you want to rationalize that. Multiply the top and bottom by root 2. You get root 2 over 2. Just be comfortable seeing it that way. Cosine there, well, since x and y have the same value, I'm going to get the exact same fraction, 1 over root 2. And since x and y have the same value, tangent there is going to be equal to 1. Pick up handy dandy green pen, and then head over to 60 degrees, pi over 3 radians. And let's see, sine y over r, root 3 over 2. You know what's interesting? I feel like I already have root 3 over 2 on this paper somewhere. Whoa. 30 and 60 are complementary angles. And sine and cosine were equal to each other there. How about that? See, cosine is 60 degrees, x over r, 1/2. You know, I feel like I've already got 1/2 on this paper somewhere. Yo. Sine of 30 degrees was 1/2. That's equal to cosine of 60 degrees. Again, complementary angles. That's crazy. And tangent of 60 degrees, root 3 over 1. You know, that whole complementary angle result thing would have been even cooler if I had cotangent on this table somewhere. Because then it could have said, yo, more often. But what did you notice about sine of theta and cosine of 90 degrees minus that theta? They're equal to each other. So what we know is that sine of theta equals cosine of 90 degrees minus theta. And we also know that cosine of theta is equal to sine of 90 degrees minus theta. And of course, instead of 90 degrees, we could have written these in radians as well. It's the exact same statement to say it in radians. Trig identities. Cofunctions are equal to each other at complementary angles. So these statements are also true for secant and cosecant. These statements are also true for tangent and cotangent. Isn't that cool? Cofunctions are equal at complementary angles. That's what's up, nerds.